Start the recording. Hello, class. I'm on vacation. The date right now is 2/21 at 11 a.m. in California. Well, it's like 9 o'clock in California. But we're going to get started. For your lesson today, we're only going to do one section, and this is actually a really important section because we're going to be learning a very pivotal and universal concept that we're going to be using continuously throughout the rest of AP Stats. So, what you can do for me is to get into this website, onlinestatbook.com/stat-simulation/sampling distribution, and you're going to be able to use this applet to help us understand the concept more. So, when you click begin, you'll see a population distribution of the ACT scores in this high school. So, when I see this high school right here, I can animate. And you can see that I have samples here, and then I find the sample distribution of, my sample size being 5. So, we're going to be able to describe the center, variability, the shape of the SAT scores. And, as we continue to do this over and over again, and if I just do 10,000, you end up with a normal distribution. So this is going to be kind of hard. Yeah. Okay. So this is going to be normal, and you're going to say approximately. Hold on. Let me adjust this. Okay. Approximately normal. The center is going to be, well, if I look at the center here, it looks like directly in the middle. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, between 16 and 17. So I'm just going to say 16 because there's 32. You can score 32. Makes sense that like half of it would be like the center. So this is my mean. And we know that we're talking about a population. So this is going to be a mu. And the last thing, variability. This is going to be a standard deviation. We see that a standard deviation for the population is going to be 5. So the sigma is going to be 5. So we want to list 5 example scores here. I'm just going to use my examples that I used previously. 13, 17, 20, 21, 24. Okay, good. I'm recording still. And the estimated blue box. So if I had these 5 like as my sample, my mean would become 19. And this is an X bar because this is a sample distribution. So the way that I found 19 was to add all these up, divide by 5, and I got this 19. So if we do this a gajillion more times, 10,000 times with a sample of 5, the blue box makes a sampling distribution of X bar. So how do we know the sampling distribution of X bar is approximately normal? The population distribution is approximately normal. So the shape of the population is normal. And we learned that if the shape of the population is whatever, like for example, is normal, we shouldn't say normal, we should say approximately normal. Approximately normal. Then we can also come to conclusion that my sampling distribution is also approximately normal. this is a lesson that we learned previously in this unit. So that's why it says like, oh, like you should see previous lessons. So yeah, if the population is approximately normal, the sampling distribution also shares the same shape. So now let's look at this more. So click clear lower 3. So I'm going to do that. Clear lower 3, which is like these 3 tables right here. And then change the distribution from normal to skewed. So I'm going to do that right here. Normal is going to be skewed. And you see how my population here is now skewed right. So what is the shape of the distribution for the population? Why does this distribution make sense for our arch rival Rockford? So they're just pretty much asking you like, what's the difference between having a population normal versus skewed to the right? And well, first of all, let's answer this question first. What is the shape of the new distribution? This is skew, right? And I'm going to use an ly word here. I'm going to say not roughly, but approximately. So why does this distribution make sense for our arch rival? So based off of the context here, well, I didn't really do a good job telling you the context, but in Rockford, a lot of people did bad. So we can say that most people from Rockford did poorly, but a few did well. And if I look at the distribution again right here, like it doesn't like over here, like in the higher spectrum of our grading system, you can see that there's people here, but it's just not as many. So if we change both the bottom drop down to mean, which is like here, good, mean, and one should be n equals 2, and the second should be n equals 25. So we're just trying to compare what would happen if my sample size is 5 versus 25. So we're going to take 10,000 samples here. So boom. And how do I do that here? How do I do this here? Versus 25. Oh, mean 25. Here we go. Boom, like this. So you see how it's skewed here, but it ended up becoming a little bit more normal, but it is still like, not as skewed, right? But you can tell that this one has a bigger tail on the n equals 5. And you can see that over here, it looks very similar to a normal distribution because of my sample size grew. So that's an observation that I did. So describe the shape of the distribution when n equals 2. So we can say not strongly, roughly, skew right, because it looked more normal, but it wasn't completely normal. But it's definitely getting towards that normal shape because of my sample distribution. So roughly skew right, but not as skewed right as my population distribution. So describe the shape of the sampling distribution of x bar when n equals 25. So this is approximately normal. And The reason why that is because the greater your sample size, the more normal it's going to become, because your your standard deviation is going to be less, if that makes sense, because of our standard deviation equation, which is, of course, a standard deviation of x bar is equal to the standard deviation of the population divided by the square root of n. So if this gets bigger, the denominator gets bigger, then the standard deviation is going to get smaller. So our standard deviation is going to be a little bit more concise. So a safe way for AP Stats for you to assume that if it's going to be approximately normal is when the sample size is large. And a number that I like to use, for AP Stats is like n is greater than or equal to 30. You can say like 25 to 30. 25 to 30. The sampling distribution is approximately normal. The sampling distribution is approximately normal. So that's a safe thing for you to do. If your sample size is large, then you can assume that it's approximately normal. Not is normal, but approximately normal. So this is our main topic, or the main thing that we're going to be learning, or that we learned today, which is the central limit theorem. I misspelled that. Theorem. And we're going to be using this a lot. And the reason why we use the central limit theorem a lot is because this really points back to chapter 1, which is like using the z-score to find the area, which is pretty much the probability. So that's why we're going to the central theorem limit enables us to use previous learning into our current learning. So this is going to be very used heavily on AP Stats. So we're going to be always referring to the central limit theorem as CLT. So the main lesson of today is really to understand that the bigger our sample size, the more normal it's going to become. So when we do our learning targets here, we have two. So the first one is going to be the central limit theorem. And of course we call it C. Come on, pencil. Oh, fine. CLT. I don't know why it won't erase. And this is a sampling. The sampling distribution of x bar is approximately normal when a sample size is large, such as like n is greater than or equal to 25/30/40-ish. I'll just put 25. This is super big because if you can assume that, or it's approximately normal, then we can use the z-score, which is x bar minus mu divided by the standard deviation. Then you're going to find the z-score. Then you're going to go to table A. then you're going to find the probability or like the area of a distribution, because all distributions are going to be based off of the total area has to equal 1, because 1 is representing 100% of the outcomes, which has to be true. Learning target number 2. I just want to talk about the normal distribution again and how we're supposed to be labeling this. So if I draw like a normal distribution very ghetto-like, like this, mine's not that good. We can always label our mean. So this will be our mean. This is our mu. And let's say, for example, this is going to be my X bar right here, which is the context of the question. Most likely, the question is going to be from giving you this. So this is a given, most likely. And let's say that I want to find like this area. First, I need to label my graph, or my table, I guess. So this is a sampling distribution of X bars. And of course, we have to label it. The n for normal is going to be mu, comma, standard deviation. But the standard deviation is going to be standard deviation divided by square root of n. The reason how come we can use the population mean is because we learned that the population mean is going to be similar to the population the sample distribution mean, and this of course is the standard deviation for samples, which is also known as standard deviation of x. And of course we're going to use the area the things that we talked about above. Nice. So check your understanding. I can help you out with a little bit of this. So check your understanding. Among iPhone users who share their data with Apple, their weekly screen time is skewed to the right with a mu of 13.5 and a standard deviation of 3.75. That's kind of low, to be honest. A random sample of 100 users are selected, and the mean weekly screen time of a sample is calculated. So describe the shape of this the sampling distribution of 100 people. Since this is greater, so n is greater than or equal to 30, we can assume that this is approximately normal. So I would say, because like if you have like this in word form, this is pretty good. So find the mean and standard deviation of the sampling distribution. You're going to use the mu of the mean of the sample is pretty much the same as the mu, and the standard deviation of the sample is going to be the population standard deviation divided by the square root of n. So I'll let you do that. Also note that we can use the 10% condition, or the 10% rule that we like to say in my class. And there's something that you can assume here to help you out. Just know that this is Evan Rich's question every single time. So what can you assume with the 10% condition? And lastly, calculate the probability between 12 and 13 hours. This is going to be a distribution, like a mean distribution. That was really bad. So they're asking between 13 and 12. So if this is 13 and 12, you're finding this. So I'm not going to show you how to do that, but I hope that this diagram helps you. So n is going to be 13.5, comma, 0.0. I'm not going to tell you this one. And you can find this from part B. And of course, you're going to use the z-score. The z-score formula. All right, I'll see you guys next time. You have another video coming along on Thursday. So I'll see you then. Later, guys.